Hello guys, welcome to Backbencher Studies channel. In the last video, we kind of introduced the frequency response, how we can derive the frequency response of a system. And we also saw that for an LTI system, how the output magnitude varies and as well as the phase of the output varies with respect to the phase of the system's transfer function or systems phase. So let us give the input as a sinusoidal term, which you can see over here, r of t equal to a into sine of omega t. So if we give this input to this system, which is having the transfer function as g of s, then how our output should vary, we will be seeing that. So we have the r of s, the Laplace transform of this signal as a by we actually have omega by s square plus omega square over here. So that is how we find out the Laplace transform. And if we have this transfer function g of s, then we have the output as the multiplication of Laplace transform of input with respect to the transfer function over here. If we kind of do the inverse Laplace transform, and if we find out the signal output signal in time domain, what we have is a into modulus of g of j omega. This is the magnitude of this frequency response. Or if we substitute s equal to j omega in this transfer function, we have the frequency response. And that frequency response is a complex number whose magnitude is magnitude of g of j omega over here, which is multiplied with this impulse input magnitude, which is the output magnitude over here. And we have the phase of this g of s that is being added with the phase here. The input phase is actually zero because we don't have any phase term added over here. So this phase term of this complex function, which is the frequency response of the system, is getting added with this over here. So the output will be a sinusoidal term with a varying phase over here with respect to the frequency. That is how that will be varying is based on this transfer function and the frequency response. So moving on, we need to analyze how the first order system, how it will give the frequency response. So let us start our analysis for the first order system. So here we have a first order system with the time constant as tau and DC gain as k over here. So it is a first order system because the denominator polynomial has the highest power of 1 over here. So this is the transfer function of the first order system. And if we substitute s equal to j omega in this equation, then what we have is the frequency response of the system. So the frequency response of this system, first order system, is k over tau into j omega plus 1. So this is kind of a complex number. So if we see that this complex number, then if we find out the magnitude of this complex number, then we have k, which is the real number, the magnitude comes under over here, and we have the complex number in the denominator. So we need to take out the magnitude of this complex number, which is 1 square plus omega square t square. So if we find out the phase for this complex number, then what we have is in the numerator we have a real number, so the phase will be 0, and the denominator phase will get subtracted with the numerator phase. So the denominator's phase being omega tau by 1, which gives us tan inverse of omega tau over here. So if we substitute this, if we substitute these expressions of modulus of g of j omega and the phase expressions, with this output, if we gave the sinusoidal input which we have derived previously, we substitute that, then we have this kind of expression over here, which is the magnitude is depending upon the omega, and the phase is also depending upon the phase of the transfer function. So this is how we can analyze the first frequency response of the first order system. So if we continue doing this analysis for the second order system, we have the closed loop transfer function of the second order system as omega n square divided by s square plus 2 delta omega ns plus omega n square, where omega n is the natural frequency and delta is the damping factor. So if we substitute s equal to j omega in our transfer function equation, then what we have is the frequency response of the system. So if we analyze these kind of systems with this kind of analysis, if we square this, we have minus omega square over here, and if we take out omega and square from the denominator, then what we have is this kind of expression with a real and imaginary parts in the denominator. So the transfer function, overall transfer function, will be looking like this uh, numerator with a real value in the numerator and denominator with a complex number having a real and complex parts as well. So if we find out the magnitude and phase of this, then we will be sure we will be getting the output as as follows. So if we substitute omega by omega n equal to u in this expression, then what we have is the frequency response expression in terms of u. So if we find out the magnitude, we have this kind of magnitude over here, and we have this kind of phase over here, which is dependent on this damping coefficient delta and this uh, normalized frequency with respect to the natural frequency u. So this is how we can analyze the first order and as well as the second order of the systems. So that's it for today, guys. If you have learned something new in this video lecture, please do like this video and please do share this video. And if you are new to our channel, please do subscribe to our channel. That's it for today, guys. Thank you.